All right, so let's get started. My name is Agrin. I'm from the research team at Peltarion. Um, Today, we're going to talk about deep learning for audio, and music in particular. So what we're going to do is we're going to spend a lot of time on today's main topic, which is going to be taking so our main topic today is going to be music tagging. So we're going to spend quite a lot of time trying to understand how difficult of a problem it is, and we're going to see if we can understand how deep learning can help in what we did. Around this will be a broader discussion around some things in images that make computer vision models like CNNs so incredibly powerful and useful. And these properties, we'll see, are not actually there for audio anymore. So that's an interesting situation. Now, I'm not someone who's an expert in music. I'm not an expert in signal processing. But what I'll do is I'll share some of the insights we picked up along the way as we worked in this application for the past year. So let's get started. Has anyone here built an image classification model? Anyone? That's a lot of people. Great. Okay, has anyone built an image captioning model? A few people? That's good. Since we're in Gothenburg, has anyone built computer vision software for self-driving cars? I thought that was going to be half the room. So if you've done any of this, you've probably worked with convolutional neural nets. These are called CNNs, and they're hugely successful for computer vision. Unreasonably so, one might argue. And we're going to look at some of my favorite examples that really illustrate how this is the case. We're going to start by looking at a very, very well-recognized scenario. So we have an image here, which we call the content image. This is an image that we want to recreate in the style of another. We have several different pictures that define different styles, and we want to transfer the content image to be in the style of the other image. You get really interesting results when you do this, but how you do this is the interesting part of what we're going to talk about. So how you do this is you take a model that has been trained on the task of, say, image classification. So a model that just simply understands content in images. Now, it turns out that for some reason, some of the outputs in your network will tend to correlate well with the style that is present, and some will tend to correlate with the content. And if you build a simple optimization problem where you optimize the content such that it looks close to the content image and the style so that it looks similar to the style image, you get these images. So all this is really is optimizing these images to fulfill those criteria. And that's pretty weird. Like, we didn't train a model to do this. We trained a model on image classification, but it can do this. So it seems to fit very, very well for this problem. It seems to fit well for how images work. Another example that's less common is deep image prior. Here we do something very similar. But this, I would argue, is even stranger. Here, you take an image and you say, I have some type of artifact in that image. I want to remove this artifact. It might be, let's see, it might be text. It might be that I want to remove a part of the image. And it might be other type of artifacts. And the way the authors here removed all of these artifacts is by simply setting up an optimization problem where you feed random noise through a neural network, a UNet, and you try to recreate the original image. This imposes a prior on the type of images that can be created, and this prior is so powerful, in fact, that you can remove these artifacts. So all of them use essentially the same method. And that's really weird. Like, if you really thought about what I was saying, I told you that we optimize the neural network to do this, right? So I don't actually have any weights in the neural network. I haven't trained it. It's the mere fact that the structure is there that imposes this prior. It is the structure of the CNN that is so well suited for images that makes this possible. Do we have anything similar for audio? Before we dive into this, we're going to look at some representation. So how do you represent audio for a computer? Has anybody here worked with audio ever? We see a few hands up. So let's see if you agree with me. So audio, when it's recorded by a computer, is essentially a set of samples, regularly spaced, usually at least 16,000 samples a second. And you record the relative intensity of the pressure coming into the microphone. As you increase the time scale and you look at the order of minutes, which might represent a whole song, you get a lot of these. In fact, you get on the order of millions. As a previous speaker here talking about healthcare and IoT was talking about, it is very hard for models to keep track of these very, very long time dependencies. So we can say that the receptive field of neural nets tend to be much smaller than on the order of millions. How does the ear do this instead? Well, the ear doesn't really listen to individual intensities. This is sort of an engineering schematic of how an ear works, and I think this is really fun because I had no idea. So it accepts the sound waves coming into the ear, produces vibrations in your cochlea, and the cochlea actually decomposes the frequency content of the signal. Are you getting this? You're doing frequency decomposition in your ear in real time. It's really fast, and you're using this to hear. And I think that's amazing. Do we have anything similar that we could use? We have something called spectrograms. These are used in many different applications. What you do is you move a window across the signal in time, you decompose the frequency content, and you create something that looks like so, an image. So here we went from something that is an audio signal, and we created an image. And at this point, you might want to ask the question, so I have an image, can I start applying my computer vision models that were so successful? So essentially, waveform and spectrograms. Now there's another representation that's commonly used. It's symbolic representations. There are many forms of it, but it is limited to the type of symbols that you choose. So it means you can't go really outside of your tonal system. So we're going to focus on audio. Now, let's see some examples of each of the representations we chose. This is WaveNet. Most of you will have actually heard WaveNet. WaveNet is what's powering Google Assistant. And it is generating waveform, raw waveform, sample by sample. And let's hear if you recognize this. Can we get them?
By Randall Kleiser.
This is not supposed to happen. All right, we'll try it again.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
I mean, it sounds similar to what you're hearing on your phone, right? It's pretty natural, it's a pretty simple model, and it sounds great. Now let's hear how it does for music. This is piano, generating sample by sample. Pretty interesting. It sort of seems natural, but there's no structure in there. And this really demonstrates the key problem of working with direct waveform, which is it's really hard to have these long time dependencies, and this sort of breaks down the generation. Let's now look at an example with spectrograms. This is doing source separation. It is a model that's very similar to computer vision models, taking spectrograms, essentially images, treated as such, takes this content, and separates into vocals, drums, and bass. So there is definitely some leakage in there, right? It is not doing perfectly well of a job. But what's really interesting about this is a repurposed computer vision model, essentially. This is taking what is so useful for computer vision and applying it to audio. And it's really cool that you can just do this and get this output almost immediately. So that's pretty cool. Now we have, okay, so we can take, if we pick the right representation, we can use computer vision models. There are waveform models that we can build as well, but they're a bit trickier. Okay, so that's pretty cool. Now that we have this sort of background knowledge, we're going to get to the main problem today. So that is the problem I promised to talk about. It is tagging of music. This we did with Epidemic Sound, and whenever I introduce Epidemic Sound, I love to do the intro like this.
Hey guys, what's up? This is Alex. So today I want to share with you what I believe to be arguably the most important pasta dish of all Italian cuisine. Nothing short. And in
Okay, so why did I show you that? Did you hear what was in the background? Did you hear the music that was in the background that elevated the quality of the content? That music comes from Epidemic Sound. So what Epidemic Sound does is they provide music to content creators, be it on YouTube or television production and so on, and make it available and easy to license. They have a massive set of data that we got access to that they actually own. And the fact that they own it means that we can do very interesting things with it. We've, for example, created a data set that's available on our platform that one can use. But there are some more features, which is the quality is really high. We have DVD quality, we have separation into stems, and very importantly, we have tags for all of these. And they're tagged by a small set of curators in a way that's supposed to make it consistent. So the way a content creator actually finds this content is by going onto Epidemic Sound's website, picking which genre or mood and so on that you want to have, and then finding songs that way. Now, setting these moods, if you think about where they come from, setting these moods are done by curators, and it's actually a very, very difficult problem. And now I would really like your participation, because what we're going to do is we're going to look at how difficult it is to perform this problem. So please, if you can, bring out your phone and participate, and we're going to do music tagging live right now. So please get ready, and then we can get the music started. Now, please assign moves. Some people more quick to make up their minds. So a lot of you think this is busy and frantic. Let's look at what the data set shows. So, angry and chasing as defined by the data set. So what does this mean? What is the point of me showing you this? The point is basically, this is a subjective thing. You have 21 different moods to pick 3 from. There are a lot of different combinations that you might want to pick. Some of them might be more wrong than others. But in general, this is a very hard problem to be consistent in. Let's go back to the original slides and pause the music. Oops. Okay, so as we said, we get a broad distribution over what people think is right. And nobody is the correct person to really say this is true or that is true. The point is, it is difficult to set these moods. They're very subjective, and getting them consistent is hard. What can we do to make this easier? What can we do to make the curator's life easier? You set 21 tags. The actual curator has on the scale of 150 to pick from. That's a pretty hard problem. So we set out to help Epidemic Sound with this, and what we did is we built a model for content-based tagging. So that is doing multi-label classification based on spectrograms. So just as we did before, we take a computer vision model, essentially, apply it to data that is audio, and then train it as we would if it was a computer vision problem. Repurposing, in a sense. Image, model, output. This is really exciting. I know it sounds sort of boring, like we're doing classification, but it's really powerful. All of a sudden, this opens up possibilities to work with audio. When we look at how we do, we're pretty happy with this result. We have an AUC, area under curve, for the ROC curve at 0.84, which is very comparable to the actual authors. The area under curve for the precision recall curve is a bit on the lower end of what we would like. But this is not meant to actually define the taste. This is meant to assist the curators in surfacing tags that seem relevant for the content, making their life easier. So cool. But I kept telling you that we can take computer vision models and repurpose them for working with audio. And this might be true, but if we look at the properties of audio and compare it to how image data looks, it is actually quite different. Does it even make sense to use the same type of model? Do we have any assumptions that break down? We're going to look at some of these questions and see if we can answer them. So I've picked 3 things that I think are really important, that are properties that exist for images but not for audio. So the first thing is images tend to be equivariant with respect to translation. That's a long word. It's a simple meaning. I have an image, I have a segmentation mask. If I move the image, the segmentation mask probably moves the same. So I have this relation. I get the segmentation mask from the image, or I translate the image and then get the segmentation mask. I get the same. Does that make sense? Sort of. It turns out that CNNs, convolutional neural nets, their outputs are actually equivariant. So they really match image content on this. If we take Poseidon and move him across the input field of MobileNet v2 and look at the first layer activations this is kernel 1, we see that indeed we have the same relation as before. We have equivariant outputs. We might as well translate the output. Now, of course, this is a truth with some need for modification. As we go deeper into the network, this gets further and further away from the truth. And we can look at the sensitivity with respect to translations and see that actually as we get further into the network, we are less and less accurate in that regard. But if we look at why equivariance is important, it's because it actually allows something that is commonly called weight sharing. So it allows the kernel that is set to detect an edge there to actually inform how edges should be detected elsewhere. And this is a very powerful feature of CNNs. Since it's so powerful, one might ask, do we have the same for different areas? And we do. We have spherical CNNs, for example, where we're equivariant with respect to the orientation of the input sphere. We have this for graphs, and we have this for general groups. But for music, that is no longer the case. And we need to rush a bit, but if we look at another property, invariance, invariance is very related to equivariance. That is, if we move Poseidon, he is still Poseidon, right? The image is, the class of the image is invariant with respect to translations. We can do flips as long as we're domain, as long as we take respect to the domain, so we can't flip all images. For audio, it doesn't really make sense to flip them. We can't really do rotations and so on. And this means that augmenting data and exploiting invariance, creating more data, becomes much more difficult for audio. We don't have the same large palette of things we can do. And finally, summarizing data is a lot harder. Images we can glance through quickly. Time series, as long as we know the different values, we can look at very quickly. Same goes for video. But for music, for audio, we're not really in the same situation. You can see some things, but not at all on the same scale. Presenting this and playing audio had its challenges in itself. So essentially, here is a backlog of things that I think are very important to address at some point when working with audio. Whenever I do this, people always ask, oh, so Agrin, when are you getting to the solutions? We're not really getting to the solutions in this. This is an open field, and I really hope for people to actually start working on this. And to recap, we can do a lot by repurposing computer vision models. Audio behaves differently, and it would probably be wise to consider how it does that differently. Thank you so much for listening.
So if anyone has any questions, feel free. No questions? Oh, question in the middle, right? Oh, just wait a second for the mic.
So has one-dimensional convolutional neural networks been used for audio as it has for text, for example?
What was the last part of your question?
One-dimensional convolutional neural networks has been used for text, which is also somehow some kind of time series. Has that been used for audio?
So the question is if one-dimensional convolutions have been used for audio, and yes, they have. So one of the first examples we listened to, WaveNet, is one-dimensional convolutions. They do some tricks to actually handle the massive, massive scale of audio, but it is exactly that. Thanks.
Any other questions? Then we have, first of all, thank you, Agrin.
Thanks.